Okay, so we have seen how trigonometric functions and hyperbolic functions generalize when we have complex variables. So in this lecture, we will look at how to find inverses of these functions. So the problem we consider is, suppose we are interested in finding, you know, that value uh, of z, which whose sign is a certain complex uh, number, whose sine or a cosine or whichever trigonometric function you're interested in, or a hyperbolic function, is it possible to work backwards? And so it turns out that it is possible to find such a complex number, but in fact, in general, there are going to be lots of complex numbers all of whose signs are the same, right? So we will end up with what are called multi-valued functions, and these are all connected to the log function and its multi-valued nature, right? So it is some of these properties that we discuss in this lecture. Okay, so suppose we want to invert the sine function. So in other words, we wish to find a complex number w whose sine is equal to some complex number z, right? So we want to find sine inverse of z, right? So we can call this as sine inverse of z, right? So we are interested in finding a w such that sine of w is equal to z, right? So, but sine of w is nothing but e to the I w minus e to the minus I w divided by 2i, and we can rewrite e to the minus I w as 1 over e to the I w, and then we can collect these terms in an appropriate way. So which is, you get e to the I w the whole squared minus 1 then divided by 2i e to the I w. So thus we have actually a quadratic equation. So if you bring this e to the 2i e to the iw to the left hand side, you have a z here, and so you bring all terms together onto one side. So then you have e to the iw the whole squared minus 2i z times e to the iw minus 1 equals 0. So this is a quadratic equation in e to the iw, right? So w is an unknown, so e to the iw is an unknown, but this is really just a quadratic equation in e to the iw, which we know how to solve, right? So the solution is nothing but uh, you know minus b in this case is uh, 2 2iz, so plus or minus. So we don't have to explicitly write down plus or minus, because we understand that this function is a multi-valued function, right? So to the power half means both plus root and negative root, both roots are allowed. So we have 1 minus z squared the whole power half, there's an overall 2 which comes out, and then you divide by 2, right? So you can work this out carefully, so and convince yourself that indeed this is e to the w is just iz plus 1 minus z squared the whole power half, right? So this I have said, and I emphasize again, is to be thought of as is really a multi-valued function. There is a plus sign or a minus sign, both values are allowed. So already there is a multi-valued nature to this, and now we're also going to have to take a log on both sides. So in fact, to find w, right, so we have to take the log of this whole stuff and then divide throughout by I, and that's going to give us a minus I times log of iz plus 1 minus z squared to the power half. So sine inverse of z is defined to be this function, right? So immediately we see that there are actually two sources of multi-valuedness in this kind of a definition of an inverse function. So inverse functions of this kind typically do have, they are naturally endowed with this kind of multi-valued nature, right? So I mean, this relates to the fact that the function that you started with itself has a periodic character, right? So there is a repetition of certain values which keeps coming back, and therefore indeed when you go when you invert a function of this kind, surely there is going to be multi-valuedness. And so the square root is is one kind of it's a bi-valued nature for this function, and then logarithm function actually gives infinitely many values, right? For a given z, there are infinitely many values of which correspond to sine inverse of z, and this infinite multivaluedness comes from the log function. Right, so there is a way to make this single valued by considering what is called a specific branch of each of these functions. Right, for example, we can choose for the square root function, we can take the positive square root. So then we say it is the positive branch. And for the log function, we have seen that often it is useful to work with what is called principal value. Right, so if you look at it in that way, then you can associate a particular value for sine inverse of z. So let's look at an example where this multi-valuedness of this function becomes apparent. So suppose we wish to find sine inverse of minus I, right? So then we would have to work out, according to this formula, we would have to work out minus I log of 1 plus square root 2 and minus I log of 1 minus square root 2. I have explicitly made the plus sign and minus sign separate. I mean, we understand square root 2 to be plus square root 2 when we are working with real numbers. So these are the two values for sine inverse of minus I, and each of them has a log, so there are infinitely many different values for each of them. Right, so let's look at how is there a compact way to write down all these different values. Now, so the square root 2, of course, it comes from the fact that when I do 1 minus z squared, I have to do 1 minus z squared. Z is minus I, so I squared is minus 1, so that's going to give us square root 2, right? So, and we have a 1 sitting here. So indeed, there are these two different values, but let's look at log of 1 plus root 2 is actually nothing but, it's convenient to call this ln of 1 plus root 2 to refer to the value that we ascribe to the logarithm of a positive real number, the usual value that we ascribe. But in fact, there is also this freedom of adding 2 n pi I, right? As we have seen, it's a multi-valued function. So in general, if you write log of any number, including a real positive number, it's not just the usual number that we ascribe to logarithm of a positive number, but in fact you can add 2 n pi I for free, where n can be any integer, right? So this is what we mean by this quantity. So let's also try and work out exactly what we mean by log of 1 minus root 2. So if you look at this quantity, log of 1 minus root 2, then in fact ln of a positive real number, which is the modulus of this quantity, should be taken, which is root 2 minus 1. Root 2 is greater than 1. And then, I mean, so you can think of this as log of root 2 minus 1 times minus 1. And then you apply, the rule that log of some quantity times some other quantity is log of the first quantity times plus the log of the second quantity, which log of minus 1 will be just 2n plus 1 times pi I. In fact, even here you can think of this as log of 1 plus root 2 times 1, which is log of 1 plus root 2 plus log of 1, and then log of 1 is actually 2n pi I. It's not just 0, right? So you have, it's a multi-valued function. So we can also, if we look at this quantity ln of root 2 minus 1, it is something which we can rewrite in the following way. Ln of root 2 minus 1 is actually nothing but ln of 1 plus root 2, right? So you can verify this. And then 1 over 1 plus root 2 log of this, ln of this is actually nothing but minus ln of 1 plus root 2. So in fact, there is a way to rewrite this back in a form similar to the first quantity. So log of 1 minus root 2 is in fact nothing but minus log of 1 plus root 2 plus 2n plus 1 pi I, right, where n can take all integer values. So you get all these odd factors of pi I here, and you get even factors of pi I here. And so you have this same quantity here and same quantity here, except that now you have a minus sign. So we can combine both of these together and write it in this form, right, and allow, instead of saying 2n plus 1 times pi I and 2n times pi I, you can just say n pi I and allow all integers and just take care of the sign change involved here. If n is even, then it must be plus, and if n is odd, it must be minus. So in fact, there is this compact way of writing log of 1 plus or minus square root 2. And then we can go ahead and plug this back into the original multi-valued, two different values that we gave, and each of them themselves come with all these free degrees of freedom in terms of n. So in fact, we have this final result, sine inverse of minus I, right? We should recall that there is this minus I sitting also, which we need to tag along. So sine inverse of minus I is actually n pi. So minus I times n pi I is going to be just n pi. Then minus 1 to the power n times minus 1. It's going to become minus 1 to the n plus 1. And then we also have this I times ln of 1 plus root 2, which is a natural logarithm of this real positive number 1 plus root 2. Right? So we see that it's quite subtle, in fact, to take the inverse function. Sine inverse is one example we have looked at, but in fact we can use a similar method to define inverse, the other inverse functions. So cosine inverse of z, you can work this out, using a method very similar to the sine inverse function. You have another quadratic equation, solve for it, and you can show that it makes sense to define cos inverse of z to be minus log of z plus I times 1 minus z squared the whole power half, and tan inverse of z is defined as I over 2 log of I plus z divided by I minus z. Right? Both of these are again multi-valued functions, and there is a way to analyze these functions as well inside some single valued branch, as it is called. And in fact, within that branch, since log is a nice well-behaved analytic function, in fact all these inverse functions are also going to be nice and well-behaved within so-called single value branch. Right? So we may discuss this aspect a little more carefully at a later time. But for our purposes at this point, we just want to be aware that it is possible to define in a meaningful way all these inverse functions, and but they have this multi-valued character. So ultimately, all of this multi-valued character goes back to these log functions or square root and so on. So these are and also the arg function, which in turn is also hidden deep underneath all these multi-valuedness of these functions. Okay, so we quickly point out that the inverse hyperbolic functions can also be obtained by a similar method. So after all, hyperbolic functions and trigonometric functions are intimately connected, as we have already seen. So one can define the inverse hyperbolic sine function, sine h inverse of z to be log of z plus z squared plus 1 the whole power half, and then cosh inverse of z is log of z plus z squared minus 1 to the power half, and tanh inverse of z is half log of 1 plus z divided by 1 minus z. And indeed, these functions do have their multi-valued character. Okay, so that's all for this lecture. Thank you.